Here's an integral that gets used a lot in physics and also in statistics. Later in this video, I will explain exactly what part we get to use it in statistics, and also I will briefly mention when it gets used in physics. Now, the first thing I want to do is set n equals to 0 and try to tackle the easiest case. But that easiest case still happens to be impossible because, I mean, if you try to find the antiderivative of this, no matter what you do, use substitution, integration by parts, whatever you try, you will see that the antiderivative itself cannot be expressed as basic functions. So you need to start with a totally different idea, and it's kind of amazing how somebody thought about this. So what you do is you take this value and you take it as a square root of this times itself. Notice that the second integral, instead of writing it as x, I put y, right? But nonetheless, since after you integrate and you plug in the endpoints, it should give you the same value. These two are the same exact values. Also, we know that exponential functions are positive, so what you're getting is some positive number squared inside the square root, and therefore it should be the same as before. Now, once you are convinced that this equal sign does hold, then the next step is to express this as a double integral. And unfortunately, this means that you need to know some vector calculus or multivariable calculus to fully understand this. But if that's the only part that you're missing, try to follow the video, because later on I will be getting to parts where it's easier. So this might be the only part that you might not fully understand, okay? All right. So going back, we can just multiply e to the negative x squared and e to the negative y squared together to make this single exponential function. And we can put the dx inside and dy outside, and you end up with this double integral. And this double integral is actually finding the volume under some surface like this one. So what I did was I took the graph of z equal to e to the negative x squared minus y squared into some online 3D surface drawing program. And you can see that when x is near 0, it gives you 1. So the peak value is 1, but then because as x and y becomes bigger, you get e to some negative of large value that's really close to 0. So it rapidly decays to 0. That's the graph that you get. So we're interested in the volume under this surface. And in order to actually compute this, you will need to use polar coordinate systems. Okay, a polar coordinate system uses r, the distance from the center, theta, the angle from the positive x-axis, to represent any point on the xy plane. And again, in multivariable calculus, you learn that dx dy is r dr d theta. And in order to cover the entire xy plane, you need the radius to go from 0 to infinity, because as you go far out, the radius can be as big as you want, right? And because you're going full 360 degrees, the angle theta should be from 0 to 360 degrees, which is 2 pi in terms of radians measure. All right. Now, if we use these formulas, we can rewrite negative x squared minus y squared as negative r squared, and dx dy will be changed into r dr d theta. And because r goes from 0 to infinity and theta goes to 0 to 2 pi, this is what you get. And the amazing thing is now, because of this r, this formula can be integrated by doing the u substitution. You just simply have to do u equals to r squared, and then it's possible to integrate this. Now, I'm not going to spell out the u substitution. You can try it yourself, or you can just look at the final result and verify that if you differentiate this with respect to r, the chain rule gives the derivative of negative r squared outside, which is negative 2r, negative 2, and negative 2 cancels, and you do indeed get this as the result, negative e to negative r squared r as the result when you differentiate this. And then once you have this, then you can plug in infinity. E to the negative infinity is 0, so you don't get anything when you plug in infinity. When you plug in 0, you get 1, but you're subtracting the negative 1/2, so you end up with positive 1/2. Okay, so we have this positive 1/2. We're going to integrate this. Integral of 1/2 is 1/2 theta because we're integrating by theta. And then you plug in 2 pi and 0. When you plug in 2 pi divided by 2 is pi. If you plug in 0, you don't get anything. And that's how you get this result. And it's kind of cool how if you just hang on to the one-dimensional integral, it seems like impossible, but when you pass it to a double integral, suddenly you can do the integration. So it's kind of strange. Anyways, this is what we get, and now we are going to use this to further calculate integral of e to negative ax squared dx. Now, if you compare these two, you see that all I'm doing is I put an a there. Okay. Now, why would I want that? Well, you'll see in the next slide. It's kind of cool. All right, but let's try to do this integral. Well, this one is not that hard because you just have to do u substitution with u equals the square root of ax. And what happens is that this will then become negative u squared, because if you take u squared, you end up with a times x squared. So this much is exactly u squared, right? And then if you apply d both sides and divide by square root of a, you end up with dx equals 1 over square root of a du. And therefore, the resulting integral is this. So if you take this and do this u substitution, this is the resulting integral. And because this part is exactly same integral as this one, which is square root of pi, multiplying this with the coefficient 1 over square root of a gives you square root of pi over a. Okay, so that's the result of this integral. This integral gives you square root of pi over a. Now, before I actually do further calculation with this, I want to make one more comment, that when you take a as 1/2, so if you take a as 1/2, that's same as dividing by 2. Then if a is 1/2, pi divided by 1/2 is same as pi times 2. So we get this result from the above, with a being 1/2. And this actually shows that if you divide by square root of 2 pi to the left side, then we know that this function, which is always positive, also has the property that if you integrate from negative infinity to positive infinity, you get 1. And if the integral from negative infinity to positive infinity is 1, you call that a probability distribution function. And this specific probability distribution function is called a standard normal distribution. Because if you actually computed its standard deviation, you end up with 1. So for statisticians, this 1 with 2 is the correct one because it has the standard deviation 1. On the other hand, physicists like something that's easier to write, so they just like this one without the division by 2. Okay, so that's some extra thing I wanted to say. Now let's move on. So we have this result, which you can rewrite it as a to the negative 1/2 power, because square root is same as 1/2 power, and being in the denominator, you have this minus. There is this famous Feynman's technique, which is that once you have some integral with some parameters, free parameters in there, then it allows you to differentiate both sides by a. And now for mathematicians, this might be a little crazy, because mathematicians are really careful with bringing the derivative inside the integral. But Feynman was a physicist, so he didn't care. So you can just put the derivative inside. And assuming that that can be mathematically justifiable, which it is, I think it's by something called the dominated convergence theorem. I think you can do that. But anyways, assuming that you can do that, we are going to differentiate both sides by a. And if you think about this function as a function of a, then negative x squared is the coefficient. So if you differentiate this inside function by a, you end up with negative x squared as the artifact of the chain rule. Chain rule gives you something that's multiplied outside, right? It will give you negative x squared by the chain rule. And on the other hand, on the right side, the power rule says negative 1/2 should be stepping down, and you have to subtract 1, and negative 1/2 minus 1 will be negative 3/2. If you recall what we were trying to do in the beginning, the very first title was x to the 2nth power. And what we have just done is x to the 2 times 1. So that's like x squared where n is 1. That's done. Okay. So this is a pretty important result for us. This is what we are trying to get. The only problem is that I don't like this minus, so let's multiply by negative both sides. And here is the desired output. And actually, to answer the question in the title of this video, you should set a as 1. Okay. But we're not going to stop here. Notice that if we differentiate yet again, another negative x squared will come down, right? So we can just keep doing that. We can differentiate this thing, and another negative x squared will come down, and it'll give you negative x to the 4th, and you multiply by negative, and this is what you get on the left side. On the other hand, when you differentiate this by a, negative 3/2 will come down, and because we are multiplying by a negative sign, you end up with 1/2 times 3/2 times this with a to the negative 5/2. Again, negative 3/2 minus 1 is negative 5/2. All right. So you do that again. You differentiate again. You negate it. You end up with this. And at this point, you will probably be able to find the pattern. So what is the pattern? The pattern is that you always get 2 in the denominator, and you get the products of all the odd numbers until this value becomes 1 less than this power. Okay, so if you observe the 6 case, when it's 6 and this 5 is 1 less than 6, right? So you stop right there. So when this is 2n, you stop at 2n minus 1, and then this number is always 1 more than this 2n. So that's something that you can just observe by seeing the pattern. And you can simplify it this way, where this double factorial means you multiply all the odd numbers only. So double factorial means that you skip every other number. So 2n minus 1 times, instead of the 2n minus 2, you skip the 2n minus 2 and you go to 2n minus 3, and so on and so on. So this will just give you the product of all the odd numbers, and this is what you get. Now, for this special case, let's plug in a equals to 1, because that's what we were trying to do in the beginning. We wanted to integrate this with a being 1, right? And the end result is that 1 to any power is just 1. So you end up with the simple result that if you integrate x to the 2n times e to the negative x squared dx, you end up with this. And then the next is you can also use a as 1/2 because you want to work with the statistician's e to the x squared function. So we actually want to get something that's related to the standard normal distribution. And in that case, what happens is that if you plug in 1/2 here, then that's like plugging in 2 to the negative 1 power, which is 2 to the positive 2n plus 1 over 2. So this will be 2 to the positive 2n plus 1 over 2. And the result is that that 2 to the 2n plus 1 over 2 can be broken like this, where 2 to the 1/2 power is square root of 2, and 2 to the nth power will cancel all these denominators because this is also n number of 2's. So they cancel, and you end up with this, where if you divide by square root of 2 pi to give you this standard normal distribution, then this thing called the moment is e is the expectation value of x to some power. And notice that when x is odd, you end up with an odd function times even function, and you integrate, and that gives you 0. So all the odd moments of the standard normal distribution will be 0. On the other hand, the even moments will be 2n minus 1 double factorial. And because the e of x squared itself, when the mean value is 0, the e of x squared, the second moment, gives you the variance. If you plug in n equals to 1, you get the variance as 1, which gives you standard deviation 1. So that's why that's how you can prove that the standard deviation of the standard normal distribution is 1. And it's very cool because now you know all the higher powers. Okay. And then also we get this result that we initially had. This one actually appears in physics a lot. For example, so first we can take this result and divide by reciprocal. We can multiply by the reciprocal of this both sides and get this. And often in physics, when you have to solve quantum mechanics using Feynman path integrals and so on, sometimes you have to do integrals like this, where you have this I in there. But nonetheless, even if you have the I, if you put this, if you integrate, you're going to get 1. And these are the things that you have to know.